In this video, I will present the proof of the monotone convergence theorem for sequences. I'm writing for sequences because there are a few other theorems in various areas of analysis with the same name. Here is the theorem in its most generality. It says that if a sequence is eventually monotonic and bounded, then it must be convergent. I've written eventually in parentheses because you will often find the statement as simply monotonic and bounded without the eventually. But in any theorem about convergence, you can always replace monotonic with eventually monotonic, and you just have to modify the proof slightly. What I'm actually going to prove is a particular case. I'm just going to prove that if a sequence is increasing and bounded above, then it must be convergent. And then there could be a second theorem that says if a sequence is decreasing and bounded below, then it must be convergent, and the proof is very similar. But I will only prove the first case. Here's my plan. First, I'm going to write down what the structure of the proof should be to make sure that when I write it, it's rigorous and formal. Then I will stop to think and figure out the subtle steps of the proof. And once I know that, then I will go back and write a full proof from beginning to end rigorously. Let's figure out the structure of the proof first. I begin by assuming I have a sequence that is increasing and bounded above. And I want to prove it's convergent. So here is the definition of the limit of that sequence is L. I assume you are familiar with this formal definition. For every positive epsilon, there exists a natural number n0 such that for every natural number n, if n is greater than or equal to n0, then an is between L minus epsilon and L plus epsilon. Unfortunately, if I start writing this, it's going to make no sense, because L is not given to me as part of the statement of the proof. This is not what I want. This is the definition of the limit of the sequence is L. It's not the definition of the sequence is convergent. And what I want to prove is that the sequence is convergent. So before anything, I have to say what L is. The definition of the sequence is convergent is that there exists a real number L such that, and then the definition of limit. So the first step in the proof is going to have to be to figure out what the limit is, to explain what L is. If I don't begin my proof by saying what L is, it'll probably make no sense. After that, I need to prove something for every epsilon, so I will fix an arbitrary positive epsilon. I have to say that there exists an n0 natural number with a property, so I will have to say how I construct it, and it probably depends on L and epsilon. And then I have to prove something for every natural number n, so I will fix an arbitrary natural number n. And finally, I have to prove the implication. So I will assume that n is greater than or equal to n0, and I will show that an is between L minus epsilon and L plus epsilon. So this is the structure that my proof, when I'm done with it, should have. And again, the most important step is that I have to begin by figuring out what is L. How do I construct L out of a sequence if the only things I know is that it is increasing and bounded above? Next, I'll do some rough work to figure out what the proof actually is, and then I will write it down. I begin with a sequence that is increasing and bounded above, and I have to figure out what is the limit L. Again, this is the difficult part. Can I define L entirely in terms of the sequence? This is what the terms of the sequence may look like. The sequence is increasing and bounded above. So intuitively, the terms are going to be crowding around some point, which is what I want to call the limit. But what is that point they're crowding around? I kind of want to say is the maximum of the sequence, except no, it isn't. There doesn't have to be a maximum. But I can say it is the supremum of the sequence. And that at least is a valid way to start, because given a sequence that is bounded above, I can define its supremum. So that's what I'm going to call L. And then all I have to do is prove that L is the limit. But now I have a candidate for it. So then I will take an interval with radius epsilon centered around this point L. And what I have to prove is that all terms of the sequence, except the first few ones, are in this interval. Well, L minus epsilon is smaller than L, which is the supremum, so L minus epsilon cannot be an upper bound of the sequence, because L is the lowest upper bound. So that means there has to be at least one term of the sequence, which I'm putting here in green. I'm going to call it a sub n sub 0, in there, between L minus epsilon and L. But once I find a single term there, because the sequence is increasing, all terms that come after n0 must be greater than an0, and also less than L. So once I find one term in there, the rest of the sequence after this one has to be crowded here, between a and 0 and L. And therefore, it will be between L minus epsilon and L plus epsilon. And that's it. That will complete the proof. This is not only the idea, but actually the full proof. So if you understand this part, you understand what's about to come. So to conclude, I'm going to take these ideas and write them down formally. Here's how the proof goes. I begin with a sequence AN. I assume it is increasing and bounded above. I want to prove it's convergent. I consider the set, I'm going to call A, of all the terms of the sequence. This is the range of the sequence as a function. And the sequence as a set is non-empty, because there's at least one element in it, and is bounded above. That was one of the hypotheses. So by the least upper bound axiom, it must have a supremum. That supremum, I'm going to call it L. That's what I take as L. And now my goal is to prove that L is the limit of the sequence. For that purpose, I fix an arbitrary value of epsilon that is positive. And I have to construct n0 from it. I'm going to look at L minus epsilon. And L minus epsilon, since it's smaller than L, that is the supremum, by definition of supremum, it cannot be an upper bound, so there exists n0 natural number such that L minus epsilon is less than a sub n0. And that is the value of n0 I'm going to take in the definition of limit. Now for this value, I fix an arbitrary natural number n, and I assume is greater than or equal to n0. And I need to show that an is between L minus epsilon and L plus epsilon. If I do that, I will have completed the proof that the limit of the sequence is L. And now I put together a chain of inequalities. On the one hand, we know L minus epsilon is less than a sub n sub 0, because that is how we chose n sub 0. Then, because the sequence is increasing, a sub n sub 0 is less than or equal to a sub n. And then finally, a sub n is less than or equal to L by definition of supremum. So I put these inequalities together, and also the fact that L is less than L plus epsilon, and if I keep only the things in blue, that's exactly what I needed to prove. So this completes the proof. And finally, if you look at the parts of the proof I have written in blue, they summarize the structure of the proof, which is the one I said earlier that it should be.